So we have three different aspects to lab number one, and in general we have a purpose for each lab, but that's really not the case here. We don't have a purpose in terms of a physics objective. What we're interested in here is that you learn the units of measurement so that we can make sense out of numerical results that we get in a specific problem. We need to know what the units are. And so most typically what we will try to do is convert our units, as I mentioned in the first introductory lecture, into SI units, which are meter, kilogram, seconds units. And so there'll be a number of exercises in this lab that will help you to exercise that kind of conversion process. And we'll also do some measurements. We're going to do one with a triangle that will involve some apps that you'll be able to download. And so I think this is really cool that we actually have apps that can help us to measure angles and to measure lengths. But we're also going to do some physical length and time measurements. So we'll be doing that as well with our pendulum oscillations, and then there'll be some computer simulations that usually go along with these labs that will help to distinguish the differences between mass and weight. And then we'll also look at just a couple of other results that we really already know the answer to. We know that the circumference is pi times the diameter, but we'll show that that's true with some household lab props that you'll be able to bring up, and we'll talk about how to get those together. And then there'll also be some graphical relationships that you'll do in simulations.
Okay, so that's the basic for measurements. And some other side notes. The number one thing we start with in measurements are these base units. So there are 7 standard base units as defined by NIST, and I'll have a link on our page to NIST. NIST is the National Institute of Standards and Technology, and this is the database where they store all the information on what units are what and how we define these units. So there's 7 base units, but the main 3 base units we will use in this class in mechanics will be the base unit for length, the base unit for mass, and the base unit for time. Once we get those units defined, we can make all these other derived units that we'll use in this course, like the Newton, the Joule, and some other ones that come along the way. So as far as, let's start with length. As far as length goes, we have a standard, an SI standard, which is the meter. Okay, so here is a meter. So we had to decide on what a meter is. So if we were going to do trade around the world back in the old days, everyone needed to make sure that the defined length of the meter was the same everywhere, right? Because if you're communicating locations and how much your map scale works, you need to make sure that your meter coincides to the other person's meter that you're communicating with, right? So maybe this is somebody's meter and this is somebody else's meter. Well, we need to have these synced. So how do we define a precise meter, and how do we make sure that this is exactly 1 meter? Well, the standard for length now, being the meter, 1 meter, 1m, is a certain amount of length that light covers in an increment of time. So we have this property of light. We have the speed of light. So a little side unit here. we have a value C. So we use this value C to represent the speed of light, and it's approximately 3 times 10 to the 8 meters every second. So light travels really fast. So if I turn on a laser light, it will go 3, and then we'll have 8 zeros meters every second. Okay, so we're looking at 300 million meters every second. That's how fast light travels. So the meter is based on this speed of light, which is a universal constant. What we know so far in our universe is nothing travels faster than the speed of light. So what happens is, this is a constant, and we can base a length measure off of this. So 1 meter is equal to the distance covered by light in 1, and I'm going to approximate this. This is really like 299, so we can look at the specific number. Approximately, that's my approximation symbol, 1/300,000 of a second. Okay? So the distance covered by light in that increment of time. So, did I say 300 millionth of a second? So if you have a clock that is that fast, in 1/300 millionth of a second, if you can measure how much the light, how much distance the light covers in that small increment of time, that will give you 1 meter. Okay, so that's what it's based on, and that's universal. So this is our definition of 1 meter. Okay, and then we have all the SI prefixes to base that meter on. Like if we want to measure smaller items, we got the centimeters. There's 100 centimeters in 1 meter. And then of course we have nanometers to measure really, really small distances, like let's say the wavelength of red light, we measure in nanometers, because it's really, really small increments of length. And then of course really large measurements, we use kilometers, and then we could go to megameters, and we could go to even further than that. We could take a certain amount of meters and we can convert it to something called light years, which is the distance we use to the nearest stars and to galaxies. That's a vast, large distance that we use. So length measures, the unit, the SI standard, is the meter. Okay, and we'll look at some of these, how to work with some of these length measures. In part 2, the mass measure. We have 1 kilogram. Now kilo is a prefix. It's the only unit that uses a prefix. We have a kilogram, 1 kilogram. Now, how do we define 1 kilogram? Well, that is just been recently updated. So interesting, fascinating history on that. I will put a link. But the kilogram was the only SI unit based on a physical object. It was a lump of metal in a vault in France that was slowly losing mass. So we can't have it, because if your kilogram is a little less than what it used to be 20 years ago, well, all of a sudden your gold bar values have dropped, right? So you can't have the standard of a kilogram changing. So they've redefined that kilogram, and NIST has been working on that, so you can look at the updates on what a kilogram is. All the other SI units have been based on actual physical properties, universal properties, except for this based on a physical object. So that's our mass measure, SI unit, mass measure. And the third is the time measure. And the time measure is 1 second, 1 s. And what is 1 second equal to? Well, 1 second, okay, used to be based on the length of the day, but the days have been getting longer. Back in the time of the dinosaurs, we had a 23-hour day approximately. So what's happened is the Earth has been slowing down in its spin. So you can't base 1 second on that measurement. And then we've progressed and we made pendulum clocks, some of the very first timekeeping devices out there. Well, you know, they would slowly lose their ability to tell time because they would lose some of their swing. The oscillations would slowly change, and you'd always have to wind them up and calibrate your clocks. So that wasn't very accurate over the long run either. So the most precise way of measuring 1 second is using atomic clocks, and there's been a lot of updates. But a basic cesium atomic clock, 1 second is measured as the oscillations between different levels in a cesium atom. So it takes about 9 billion oscillations in 1 second, and that's what we define as our second. So that's the basic of atomic clock. I'll have a link to that as well on our page. Okay? So this is what we want to explore and really understand these base units. And remember, these are only the top 3. There's 7 total, like the Kelvin for temperature, the mole for the amount of substance, and so on. So I'll give you a list of these online. But these 3 base units are what we're going to use to derive units. When we define a Newton, we're going to base it on meter, kilogram, and second. When we define a joule, which is a unit of energy, we'll define it on these base units. So get your base units down and you're off to a good start. And many times I like to tell students, when you're actually problem solving, sometimes if you're really stuck on a problem, you could work with your units and get the desired result by knowing what kind of units you're after. So it can be very helpful in problem solving. So one of the first things we want to do is have you find like a right triangle, if possible. You know, try to spot a right triangle. Maybe there's a right triangle sign that you have, or any other right triangle available to you. This is a nice right triangle. So if you have one of these available, that's great, but it's totally understandable if you don't. So you could make a right triangle with one of these, trace one out to measure the lengths and the angles. If not, let's go ahead and, as best we can, draw a right triangle. And the idea is not to measure out the sides yet. What we want to do is practice with that. So I'm going to draw a little right triangle on the board. And for space, I'm going to move it over here. So here's going to be my triangle. And just have some random lengths here. But it should be fairly clear what the right angle is. Okay, so I'm going to use my right angle symbol. So I'll call this side 1, side 2, and side 3. I will call this angle 1, angle 2, and angle 3. And what I want to do is measure these and write them on the table. So my sides I want to keep in centimeters, and my angles measured in degrees, or theta is our symbol. So for slide 1, I'm going to have one set of measures that I want to do with a ruler that's handed to me, a ruler or measuring tape. If you have measuring tape and they don't have the metric units on there, you might have to do some conversions. Good practice. If you have a ruler that's handy, you could do that. We also have links to printable rulers. This is a printable protractor, but you could print out one of the rulers, which is a little longer, and maybe you could make one out of cardboard. You know, you could trace it on cardboard and use those, or paste it onto cardboard, and you have a pretty good ruler you could use for the semester. Okay, so if I measure these out, what I want to do is verify some laws quickly, but really, again, this is meant to just be practice. So this is like 21.8. Side 2, we have 16.6. Side 3, we have 27.4. Okay. Next up, for angles, we want to use our protractor. And for the first set of data, we're going to use these protractors, either the protractor you have on hand or the printable protractor. So again, remember that you're measuring from the center point, that pivot point of the protractor. We're going to be using a lot of these in future labs when it comes to equilibrium, so it's important to get a handle on how to measure angles. So I have this labeled as 2, 3, this is angle 1. So I'm going to measure angle 1, place my central point here, and I get about 35 degrees. Okay, so whether you use a plastic or the printable, and the printable you'll see is works with ease. You get about 35 as well for both of them. Okay, and then angle 2, we know that should be 90, that's good. And then angle 3, let's see, line this up and I get about 53 degrees. So a little off, okay? So this is done with a ruler, printable or physical, and this is done with a protractor. Okay. Now, I'm going to have another set of data. You could use one of your apps, ruler apps here, like the ones that are found on Measuring Box, or what I have is also the ruler app. Mine is not loading correctly, so there'll be some, you want to try to download more than one app. I'm using the ones for iPhones, but if you have comparable apps that work on the Android, etc., please just write them down and state what you have been using. And in our case, I'm going to go through the second set of angles. I'm going to go ahead and use either my angle meter or my Measuring Box app. I like the Measuring Box app. Actually, I like both of them. They're pretty good. So the Measure Box app, I will load this. So here I have my Measure Box app, and I'm going to go ahead and load my Measure Box app. And I'll go to the main menu, and I have several options. I have ruler, protractor, compass, but I'm going to go to the protractor setting, and I want to open my camera. So again, this can be done on your phone. So you can see that you have a protractor. And the angle meter also has a protractor that's connected to the camera, which makes it really handy to do the angles. So I'm going to verify my second set of angles, and this will allow me to find the percent error, etc. So I'm going to do a second set, and I'm going to go ahead and use, it's usually easier when I zero these in, so I'm going to go to the 0 mark here. Whoa. So what's going to happen here is I do angle 1. That's probably the hardest part, is to line this up. There we go. I align that up and I move this other circle, and I can take a snapshot of this too. Get like 44.3 degrees, and that's for angle 1. So I actually get a larger angle in that case. using apps is definitely a lot trickier to show than just taking snapshots. So let me do angle 3 here because it's a lot easier to show on the board. So here I have that line at 0. And I want to do the interior. I go up. So I get like 52 degrees, which is really good. Okay? So the idea is I'm going to use this app to do another set of measurements, and I want to practice another app, ruler app, to make my length measures. That way you have 2 ways of doing things, and you will be asked to take some pictures of the setup. Like I could have taken a picture of my measurement of angle 3. So that will show me that you know what you're doing. Now, the next main goal here is to take these measures we have, compare them with other systems. Like we could take an error measurement, percent error between this set of measurements for a side and another set, and see how much these are off. But these are just within the same data value, so that won't tell us much. But what we can do and get a good picture of how our data is collected, how precise our data is we know that the interior angles, right, angle 1 plus angle 2 plus angle 3, we know in theory by our triangle geometry must equal 180 degrees, right? And that's our theory measurement. We can compare that theory of 180 degrees to our experimental measurement. So what we could do here in our first set of data, we would have 35 degrees plus 90 degrees plus 53 degrees. So here we have 90 plus 88. So that's 178 degrees. And we can plug those numbers in here. So we could put 180 minus 178 divided by 180 multiplied by 100, we'll get the percent error. And that will tell us how accurate our protractor measurements are. Okay, how close to the theoretical range it is. Now, we can also do that with our angle app. When we do our angle app, maybe we have even better measurements. Maybe this comes up to 179 or 181 degrees. So we would add that up, we would sum that, and we'll get another measure, and we can compare that with the actual theoretical measurement. So this will practice, you'll get some of the practice of comparing your experimental values to theoretical accepted values, okay? Sometimes it's hard to compare a measurement value with another measured value, right? It would be hard to compare this centimeter measure to another device I use for centimeters, unless they were really, really different. But here we have a nice value to compare that to, 180 degrees. Okay, so that's the very first part. The other parts that you'll be asked about this is to verify some of your trig relations. So we do know that like the sine of 1, we know that the sine of angle 1, which is, let's say, 35 degrees, must equal the opposite of adjacent. So in this case, we would want to verify. You might be asked that in some of your post-lab questions as well. Just to, again, get you the practice for doing your trig relations, some of which you'll see a lot more in future labs. Okay, that's to get started with your triangle, your measuring apps for length, and the next part of the lab will deal with mass and looking at the standard mass and working with kilograms. And what we want to do is make sure that you really know the difference between mass and weight. Mass is our standard, it's how much of a certain substance there is. And the standard is the kilogram that we base all mass by. And we use that to drive other units, like the units for force, which are newtons. Now weight, which is measured in pounds, is actually a force, and pounds is a measure of how much force. So we can convert pounds to newtons. So mass is something that doesn't change. You could take 1 kilogram, your 1 kilogram standard, which
And so one of the first things that I wanted to look at is the pendulum. Okay, now a pendulum is essentially, a simple pendulum is a mass that swings back and forth and completes a cycle in a certain amount of time. And that time, which is the time that corresponds to going across and back, is equal to 1 period of the oscillation. And so what you'll do is find some string, or you can use twine, you can use something that is a little thicker. It could be a little thinner. It could even be sewing thread, and then tie an object onto it. In this case, we've got a bolt that I have tied onto the string. And then we can allow this object to swing back and forth. Now, you can set up a stand like this, but that's not really required. If you just hold it steady and allow the thing to swing back and forth, that should be good enough. And so the amount of time that it takes to swing through 1 complete cycle is what we're going to want to plot up versus the length of the string. Okay, now the length of the string will go from the point of support to the center of the object. Okay, so in this case, since we have this big bolt, you want that length to go from where I have it supported up here with my finger to the actual middle of this object. Now how can you measure that? Well, you can measure that with a ruler. You say, well, I don't have a ruler. Well, we have that set up for you so that if you don't have a ruler, you can download a ruler and print it out. Okay, and so you have the devices that you need in order to measure the length. Now what about the time? Well, you've got almost everybody that I know has a timer on their phone. And so what we can do here then is to measure the length and then let this thing swing through 10 complete cycles. Okay? And so with 10 complete cycles, 5, 6, 7, that's across and back, 9, 10, and then hit your stopwatch again. And then take that result for the period and divide it by 10. Okay, so T total divided by 10 would equal T average. So that would be your average period for a given length L. Now, it turns out that although this may not be obvious, the period of the pendulum is not related to the mass that's hanging. And we can see that these two are swinging fairly much in conjunction with each other. If we can get the length the same, we should have a period of the pendulum that's the same. And so I could have something like this that has the exact same length, and that should have the exact same amount of time to go through 1 complete cycle. But if I change the length, let's say I make the length quite a bit longer, then the amount of time that it takes to go through 1 complete swing has expanded. Expanded by how much? Well, it turns out that the period of a pendulum, T, is equal to 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity. Okay, so G here, we want to use the exact value, 9.8 meters per second squared. And so we see then that our theoretical relationship for the period of the pendulum should go like the square root of L. And so if we were to plot the period versus the square root of L, T versus L, it might look something like that. But what we're interested in is something that would be a little easier to analyze. And so if we square the period, then that's going to relate directly to the length. So this would be 4 pi squared over g times L. And so if we plot the period squared versus L, we should get a slope to this curve that is equal to 4 pi squared divided by g. Okay? And so that's what we would expect then if we, say, take 4 pendulum lengths and measure the period. So we want to do this for 4 different lengths of the pendulum. Now you are welcome to also show that it doesn't depend on the amount of mass that is being held at the end of the pendulum. But here we see that the period relationship does not depend on mass. And so therefore, you should be able to show that the period has a square root of L dependence by just being able to plot, and this is what we call linearizing the problem, by taking the square of the period and and plotting that versus the length. Okay, and so by doing this and getting a slope that's equal to 4 pi squared over g, we should have demonstrated that our period length relationship is correct. Now what does it physically mean? Well, physically it means that if you cut the length of the pendulum in half, that should correspond to a 1 over the square root of 2 decrease. We cut this in half, that should correspond to 1 over square root of 2 decrease in the period of the pendulum. Okay, and so if we go from a longer length here, the pendulum is a bigger value. Shorter length, the period is a shorter value. It's going faster, but it means it's going through one complete cycle more quickly. Okay, but it's only going to be 1 over the square root of 2 of the original period, which is about 70% of the original period. However, if you were to, say, increase the length from this length and then go by a factor of 4, 3, 4, then what this equation tells us is that the square root of 4 is 2, so that should double the period. And so what we're looking for then is for you to be able to show that the relationship that you are able to plot up is a square root relationship between the period and the length. Now later on, when we get to simple harmonic motion, we'll derive this result. But for the moment, we're just trying to get some measurement exercises in. And so this is a way of measuring two things, really. We're measuring time. Now, why are we letting it go through 10 complete cycles? Well, because we have reaction time errors. And so if you let it go through 10 cycles, then that cuts your reaction time error by a factor of 10. So that would be the aspect of this lab that I'd like you to analyze using the pendulum oscillations.
Hello, students. Part 2 of your lab for measurements will involve exploring basic relationships and collecting data. Hello, students. Part 2 of this measurements lab will be about collecting more data, in this case data about circles, and making the measurements of circumference and diameters of circles using different methods as well, and then exploring the relationship between those two variables and deducing what the relationship is, analyzing what the relationship is, and coming up with a ratio between the two variables, a well-known ratio called pi. So we'll look at our data set, and what we should be getting from our data set is the value pi, and we'll be looking at the linear relationship that's formed. So we'll get a lot of these linear relationships, these linear regressions in our data sets for physics for a lot of basic relationships. So here's a good one to explore. And just to kind of go through the basics with you, we know that any circle has a circumference, that's a distance around a circle. So we define a center, and the distance from the center to any side, any part of the arc of the circle is your radius, and double your radius to get your diameter. So diameter is the distance from one side of the circle through the center to the other. So in this actual lab, we're going to have you get familiar with putting things together, doing some at-home experimentation and some DIY, do-it-yourself experimentation. So we want to look for circular objects. So the more circular objects you have, the better off you are. So we want at least about half a dozen for you to do. And for circular objects, like I have frisbees, you can use frisbees, plates, cups, balls, cans, and all kinds of different ball sizes, globes, clocks, clock faces. So there's a lot of circles out there. But the main thing is, what we want to get is the circumference value, and the way you get your circumference is to use a string, get a piece of string. If you don't have string available, any kind of cord or flexible material, a piece of thread. If you have clothing that's falling apart, that's great. We could use that to measure the distance around the circle. So we want to get the circumference. We measure that with a ruler, one of the printable rulers or other rulers available to you. And then we want to measure with the diameter with the ruler. So that's that halfway distance across from the center to one of the side, or the caliper app. So on my phone, I have a caliper app, and it works best with smaller items. So I will add in some pictures there for you. So here's what the caliper app looks like. And we have this blue rectangle in which we fit our object, and you could resize this and you could get the reading of the caliper there. So we want to do our diameters using this caliper app. Okay, I'll give you some instructions in our lab procedure for that. Here's a giant caliper, okay? And the idea behind the caliper is to get the measurement precise to a few decimal points, at least 1 or 2 decimal points, depending upon the caliper. This one will go to 1 decimal point. So if I have a measurement between 5 and 6 centimeters, and I want that precision of that 10th decimal place, I would use a caliper so that I could say 5.6 centimeters or 5.7 centimeters. Okay. So if we're going to get our measurements for circumference and diameter, we're going to plot that in the table. We're going to get our one measurement for circumference and our 2 different diameter measurements with the ruler and the caliper. And then we're going to get these data values, and we're going to plot these data values, and we'll see this linear relationship that abides by this function. Circumference as a function of diameter should always equal your pi, your slope, times your diameter plus 0. The nice thing about pi is that this appears any circumference, any circle you take, any circumference divided by diameter gives you this magical number pi. So this circumference divided by the diameter gives you pi, and so on. This circumference divided by the diameter gives you pi. So we're going to get as much data values as we can, and then plot this line and get a relationship there to predict the value pi as our slope. Okay, so this is like a y equals mx plus b relationship. So this is one of the models we use in algebra for linear relationships. So we have our independent variable is equal to our slope times our dependent variable. is equal to our slope times our independent variable time plus our y-intercept. Okay? So we should have about 0 for our y-intercept, but our slope should be pi, and our diameter is our independent variable, and circumference depends upon your diameter, and that makes sense. The larger you make your diameter, the bigger the circumference will be. So we have circles everywhere. So the big thing is to get these measured and come up with a value. So with your string measures, I only have a thick piece of string for the Frisbee. Cut one out, I guess. But the idea is we measure around. So let's say I get a measurement of about this much string, so I get about 64.5 centimeters for my circumference on that Frisbee, one of my favorites for disc golf. And then for the diameter, if I use my, so you want to get your center found. Sometimes it's easier to mark a center, so I look at my diameter and I get like 21.5 centimeters here. Okay. That's with my ruler. And then just attempt the caliper app. I know this is going to be a little tricky to do, but it's good to know how to do a little more precise measurements instead of just a ruler. Calipers are what we usually use in lab. And the apps they have nowadays are really handy. I know you have some limitations with the free apps, so you know, it's not as easy to use, but it's important to experiment with how those work and understand how they do give you more precise measurements. Okay, so as you can see, there's a relationship here. So I can see that this is about 3.14 rounded off. So this times 3 gives you about 64. So I know I'm on the right track. Now you take any other circle, any other sizes. So you take all these circles and get their circumferences and diameters. And what you want to do is just make a data list. Okay. The other thing that you have to make sure you do in this lab is list your objects used. Okay. And variety would be a real key to this lab. The more you have, the more different circles you use, you'll see that no matter what, how big the circle is, that relationship always holds.
Okay, and so once we have that, then you can plot the circumference versus the diameter. And so we know that 0 diameter should be 0 circumference, and so you can do this, say, in an Excel plot. Then as we go up, a larger diameter means a larger circumference, but the slope of this curve should equal pi, okay, because circumference is pi times the diameter. So this is a simple way then, by being able to measure lengths and lengths around a circular object to get the value of pi. And so that, I think, is pretty straightforward. And so I think that that concludes my section of the intro.
Part 3 of your lab will be exploring graphical relationships. Some of the general graphical relationships and the analysis that comes along with those in physics and what they mean. So in nature, we have a lot of relationships that we like to analyze. In part 2, we looked at this relationship of geometry between diameter and circumference. And if we move forward, we'll see in motion, there's a lot of relationships. There's a lot of linear relationships in motion. There's a lot of parabolic relationships in motion, right? So goes up must come down. So there's a certain motion versus time graph that's produced by the object of different objects that are in motion. So in this case, when we're looking at free fall, if I throw an object up and it comes back down, there's a way I could describe that motion mathematically. And there's other types of graphs that come up in physics. When we were looking at pendulum oscillations for time, those can be plotted using some trig functions. They're sinusoidal graphs that describe a lot of natural wave behavior and timing behavior, periodic motion. When we look at simple harmonic motion, we'll be looking at more of those type of curves. There's also exponential curves. So like if you're looking at exponential increases, we use exponential functions to analyze those type of features. We have exponential decays. So we use certain types of curves to explore that phenomena. So it's important to try to picture things in terms of graphical terms and be able to use that to predict future data sets or to extrapolate from those graphs information that we need to look for underlying theories or things that will sync up with the theory that we're working with. So we're going to use some simulations to explore these graphical relations, and we just want to know and become familiar with the most basic ones we'll run across in this course. All right, that's it for now. Let us know if you have questions, and we'll try to give you as much good instruction on the actual Canvas page and give you some tips there, but feel free to contact us for any lab questions. All right, have fun.